Welcome to our first video class experience here for 351. We're in the middle of chapter 10. Selected the YouTube video approach to kind of approximate the normal classroom experience. And so these URLs will be available on Learning Suite. We'll tell you exactly where to find them. This is intended for Wednesday, March 18th class time. So we'll be finishing chapter 10 in this class period. So your homework for chapter 10, homework 10 is due tonight if you're watching this on March 18th. And so that'll be as normal. Just upload your homework and we'll get that graded and taken care of the normal way. Now there are new things, of course. We're moved back a couple days, so we've got to give you a new schedule. And hopefully that'll show up on Learning Suite shortly. I should finalize that here this next week. Office hours, if you're in town, in small groups of you can show up and still come to my office if you need help. We'll handle help elsewise just with the Learning Suite chat or just email us, okay? So the TAs are helping still with email, so we're not holding formal recitations anymore, but they're helping out that way. So office hours that way. And then the next lecture after this one will be intended for March 20th, Friday, which will be chapter 11. Remember, chapter 11 is the last one of this next sequence of 3 chapters before test 3 coming up, so stay tuned for that. All right, very good. Let's see where we left off last time, which if you look here in the overheads here, and this is your graphic from your book. Remember, for chapter 10 here, we have the big 5, all H reactions, right? Hydrohalogenation, hydration, halogenation, halohydrin formation, and hydroboration. We'll be doing the last 3 today, going over that. They're all very similar in that the alkene, remember, acts as the nucleophile, and we got to know what type of electrophilic reagent we're using. So we'll review the first 2 that we did last time. Remember, reaction 1 here is hydrohalogenation. So I number these 5 reactions sequentially to keep you apprised of that. So we got 1 butene here with the reagent HBr, and what do we get? We get protonation out on the end here. Push the electrons. We'll get the secondary carbocation being formed. Remember, that's what type of addition then? There's selectivity involved here. That's Markov-Nikov addition. So the more substituted carbocation is formed because you put the electrophile, the H+, on the end carbon here. That's the key thing. Then the rest of the mechanism is what? Bromide anion attacking here, and we get the secondary bromide product. For what? Hydrohalogenation. Then we can have more substitute alkenes, like this trisubstitute alkene, the methyl cyclohexene with HCl now. And we get, again, Markov-Nikov protonation, tertiary carbocation. We expect this chloride right here. Hopefully, review your notes, review the book, and that first reaction should be pretty clear now, this Markov-Nikov addition with the different types of alkenes there, okay? Now the second reaction is what? Hydration. Remember, we had catalytic sulfuric acid. You don't need to say catalytic whatever, you just show H2SO4, the catalytic sulfuric acid, and then presence of water, so we're favoring hydration. It's the same mechanism, right? We're protonating out on the end here and forming the same secondary carbocation, and then water can attack. Remember, there's another step there. What do we say? The initial adduct is hydronium ion. These 2 hydrogens from water are still on there. Then we lose that proton off the hydronium ion intermediate, give us the neutral alcohol. But again, it's Markov-Nikov addition, right? The secondary alcohol is the key thing that's formed there. Now, here's that same one, same reaction 2. But now what do we have? The branched substrate here. And maybe we did some of these examples last time. Maybe we didn't, but this ties into what we looked at before with alcohol halogenation, remember, if we went through a carbocation. And if there's branching at the next door position, the secondary carbocation that forms initially can undergo what? An alkyl shift here. So I'm kind of combining a couple of the points of the mechanism. And then we're in the presence of water, so the tertiary now carbocationic can form, and then the tertiary alcohols form with that migration. So this methyl group had migrated over. Okay? So hopefully you remember that from the branching being next door to a carbocation. Remember my corollary. If it's branched and there's a carbocation, it will rearrange. And always go to the more substituted carbocation. This is an example from nature. I think I just mentioned it. I didn't show you. But this is fumaric acid from the citric acid cycle, which has an alkene right here, okay, 2 carboxylic acids. Now, we're not using sulfuric acid to do that. That would be damaging to the cell, okay, so living systems don't use that. But an enzyme is able to protonate the alkene, form a carbocation, and then deliver water. So it's the same thing. Water has been added here, and it forms malic acid, which is now no longer an alkene, but a secondary alcohol from the addition of the water there. What you might notice here is I'm drawing the stereocenter right here. And this is an enzyme, which is chiral. So the stereocenter forming right here. What is that stereocenter? Top priority, second, third? That's indeed the S stereocenter. And it's only the S that's formed there. So you may want to think about that. Well, this is a chiral catalyst now. Okay, that's different. We can go back and look at some of these others. Are any of these chiral that we looked at before? Look at the secondary bromide right here. That is a stereocenter, so it'll form as what? A mixture of enantiomers, the DL pair. This one, achiral, you don't need to worry about there. So you need to inspect the product, okay? So here's the secondary alcohol from this hydration. Also a stereocenter, so that's also DL there. This one here, you would say is achiral. Okay. But this one, because of the chiral catalyst, and you don't need to worry about that in the mechanism. We'll learn more about that in biochemistry later on. Okay. Here's a bonus reaction. So this relates here to reaction 2, hydration, but instead of using water as a solvent, what's the solvent here now? It's methanol. But we have the same catalyst, right? And a substitute alkene. So let's see if we can figure out what the product is here, just following the principles. This is not a reagent combination of the 5 key reactions. We'd call this something else, and we'll see once we figure out the product what we might call it. Well, let's go ahead and protonate there in the Markovnikov sense. We'll get the tertiary carbocation, just like before. Now, instead of water as a nucleophile, what's our nucleophile? Methanol. A lone pair can go on there. And look, so we get this with methanol, the methyl group there, CH3, and we still have a hydrogen here. We have a charge that's missing, right? What's the charge here? Okay, it's the same as with the water, right? Hydronium ion intermediate. Just go ahead and draw that. And that'd be a charged high energy intermediate. How can we get to something that's neutral and maybe stable, and maybe this product here? Well, we have excess methanol. It's the solvent. So we can imagine methanol, another equivalent here, taking off that proton and giving us what product? The tert-butyl methyl. And what is this functional group? Oxygen with 2 alkyl groups. Very good. It's an ether. I knew you'd get that. Okay. Remember your functional groups. Okay. So it's not an alcohol product like from hydration, but it's an ether. So we call this hydroetherification maybe. But don't worry about this one. This is an extra bonus reaction that's directly related to the alcohol reaction forming there for number 2. All right. Questions on that? Hopefully that's clear, pretty clear there. We have Isaac, my graduate student, doing the filming here, and the TAs will be here periodically for these video lectures, and they'll ask me questions if I'm not clear on something. And of course, you can chime in later, and I will look at the Learning Suite emails and emails sent directly to me concerning questions. But this is review, right, for reactions 1 and 2. Let's get into the third reaction here, which is halogenation now. So this is going to be a little bit different. Let's get the main event up here, reaction 3. And maybe we can stay on this board over here, Isaac. Okay. Let's make some room and get into 3, which is going going to be halogenation. So reaction 3 here, we've got bromine. Now it's molecular halogen, right? So it's bromine, Br2, or chlorine. You can do reactions with fluorine, F2. Problem is carbon-fluorine bonds are so stable, so energetically favored, you often get an out-of-control reaction. It's very exothermic. We form carbon-fluorine bonds in other ways. So fluorine, let's say, is a no-go here. It's too reactive, actually. Iodine, yeah, we'll go and form the iodinated products, but carbon-iodine bonds are much weaker than bromine and chlorine bonds. So in general, that's not a good way to go, mainly because carbon-iodine bonds are less favored that way. But let's get the main reaction up here. So looking at a halogen bond, you think, well, that's not a polar bond at all. It's two similar atoms. But remember, the halogens are very electronegative. So these electrons shared between two halogens can be polarized one way or another. So we can say they can have an induced dipole moment. So partially, when this molecule is in solvent colliding around here, this electron cloud can be perturbed quite easily to have a partially positive end and a partially negative. Remember, the delta means partial charge there. So let's see, the reaction here would be with a simple alkene. And what is the product? Well, it's the dichloroethane product. So notice, like before, the pi bond is going away, and we're forming two new sigma bonds here to form that. If we have a more complicated alkene and a bromine, Br2, okay, now remember this is the full halogen molecule. So what do you expect here? The two halogens are added across, double bond in this addition reaction. We'll get a secondary bromide there and a primary bromide there. So, you know, you might notice right away, what at this position here, that's a secondary position. So what, is that a stereocenter? Yeah, indeed it is. So we'd expect to have a mixture of an anchors, a DL pair there. All right, let's look at some other examples of this. Before we get into the mechanism will be similar. That partially positive end is going to be the electrophile, okay, that's going to interact with the pi bond there. But let's look first at this example, a cyclic alkene with bromine, Br2. It's going to form the dibromide again. But what about the relative stereochemistry now? These are two, what? Secondary bromide positions. Is one bromide going to be up and one down? Or both going to be up? Or what? What's the relative stereochemistry between the two? Well, it turns out it's this. It's one up, so I can modify the drawing here a little bit, and one down. They're always trans to each other, okay? And we'll assign R and S if we need to here. But the first thing we want to look at is this, when we talk about the stereochemistry. It's not cis on this cyclic structure, okay? So not cis, okay? Which would have the two up or the two down, wouldn't matter. But yeah, how can this work here? Well, let's look at the mechanism. So we can attack the partially positive end of the halogen molecule in that manner. So this is a relatively weak bond. It's only worth about 60 kcals per mole, so it can be broken. As these two things collide, we can break that bond, push the electrons what? Toward the electronegative halogen. So that's what's going on here. Well, let's see, what do we get then? Well, we get a bond of bromine, and we'd have what? Plus charge here on the carbocation. And we'd have Br minus, okay? Well, the empirical result is that the anti-product is formed here. You could say, well, maybe the bromide on top is blocking the approach of the bromide from the bottom. Well, it actually turns out that this is not the intermediate. What actually forms is a cyclic structure first. We call it a halonium ion. This halonium ion is actually a bridge structure. So let's see what this might look like. It'll have the alkene part here, and the bromide, you see, is on the top and the bottom. How do we form that? We'll just take a lone pair off the bromide intermediate, and what? Attack that carbocation. That puts then the formal charge on bromine, okay? That's that halonium or bromonium ion. It looks like a cyclopropane. It's strained, it's not going to stick around too long. And I'm going to draw this hydrogen down here to help figure out the rest of the mechanism, because we have bromide anion here coming in now as the nucleophile for this second part of the mechanism. And if it attacks from the bottom side of this halonium ion, it's going to break this bond here and go to what? You see, it's got then the bromine on the top and the bromide on the bottom. Okay. So that's very different here. Here's the hydrogen that was in the back, you see, and what are we going to call this? Nucleophile attacking from the back? That's similar to what reaction we've already seen? It's like what? An SN2 reaction, right? It's doing the backside attack, giving this trans dibromide arrangement here. So it's not the cis. What we always observe from these cyclic alkenes is this trans position here. And it's because it's this backside or anti-attack that gives us this resulting stereochemistry. Then we can analyze these. Is this chiral? Is this chiral? The cis one, well, that would have the near plane symmetry. We'd say that's achiral, right? Well, what about this trans dibromide here? Do we call this chiral and what? Is that a stereocenter? Is that a stereocenter? Yes, indeed they are. The achiral one, this would be achiral but meso, right? Because of the symmetry. But this one here would be what? That would be the R, and from down there, R. Well, that's just one enantiomer. You'd also form what? Some of the SS. In fact, you'd form an equal amount, which would look like this. Okay. And so assign your things. That's indeed SS. It's still trans, okay? So it's still got that. How might we form this from that same intermediate? Okay. Well, let's redraw that intermediate. What we'd have is bromonium ion. And notice the bromonium ion is achiral. It's got the symmetry going through it. So we attacked from this side here, but why couldn't we also attack bromide ion from below right there and give us what? Give us this, yes, with equal probability. So we form the two enantiomers of the trans dihalide, equal probability form of the RR and the SS, okay? But we form none of the meso from this, okay? Let's look at some more examples, and hopefully this will become a little more clear. Look at your models and analyze that. We'll go to that here in a second, but how about another example here where we've got, what, a cyclopentene. So we can do our halogenation here. And let's do chlorine this time, so Cl2. And, draw your chloronium ion. Top or bottom, it doesn't matter. It can equally form from either way. Let's draw it on the top. So I'm kind of skipping part of the mechanism there. The first step is just attack there, and then forming the cyclic chloronium ion. And now what? Attack SN2, which would be at the secondary position or the tertiary. Remember, we have this methyl group here. So which side are we going to attack? Very good. From the left-handed side, which would be the secondary side. Okay. So let's go ahead and attack from the bottom and pop that open. What do we get? We get the chloride up right there. The group is still back. We didn't do anything to that stereocenter, but we inverted that one, right? So hydrogen's up right there, and chloride is down right there. And again, that's a trans relationship between the two here. Do you have a question? Yes?
So I would think if you use the chlorine to attack from the top carbon, from the tertiary one, I feel like there might be, like, in the transition state, kind of a positive charge buildup on that carbon,
Ah,
and that would be a more stable carbocation in the transition state, so why
Yeah.
would it not attack there?
yeah, and we'd still get the trans relationship here. Okay, so yeah, there might be more buildup of positive charge there, but we do have a charged nucleophile here. We do have X minus nucleophile. So maybe it's more SN2 at this less hindered spot. You can see that. If we built up a lot of carbocation character here, chloride could maybe attack from the top or the bottom. So maybe that says it's more of this SN2, which is, I think it is at the less hindered spot. But notice we have the trans relationship here. This is a chiral molecule, so we can actually form the other enantiomer of this, which would look like what? Chloride there, methyl up, and what? Chloride in the front there. Notice that's inverting both stereocenters, okay, from there. And so that would be forming the chloronium ion from the bottom face, which we can do there. And then if we attack here, notice we have chloride in the front and that in the back. So again, this is a DL pair. Okay? So it's a little more complicated with some of these cyclic structures. I'd like to show you now one that's probably the most complicated part of this reaction. So if you thought that was a little tricky, guys, we'll see on this one here. So if you have trans or E2-butene versus Z2-butene. Let's look at both of these reactions with bromine. Okay? This one, the E, is going to go to this product. Okay? One bromide up and one bromide in the back. You kind of see the anti-relationship there with the Z alkene. Remember the pi bond's gone away here. And we'll look at the bromonium ion and see how we get at this. But what product is that? If these are trans to each other and the two ends are the same, be thinking about that molecule. Versus this one here, which will have like this. And I'll keep the anti-relationship between the two bromides here, but we've got the Z stereochemistry, the cis stereochemistry here from the 2-butene. So what's the difference between these two? Let's look at that first. So if we rotate around here, what do we see? We see bromide up, and if we rotate around here, this bromide comes up right there. So what do you notice about this molecule? Plane of symmetry. So this will be what? This will be achiral. Okay? That's the achiral one. From the E alkene, which has symmetry on both sides. But if we have the Z, we get this one. And we can rotate around that bond there also and get just another view of it. We've got the bromide up. And if we rotate around, you see to put the carbon chain in this extended zigzag, what will that happen to this bromide? It will be in the front right there. Same stereocenter. We didn't mess with the stereocenter. We maintain the anti-addition of the bromide. So that's why I say this is tricky. This one's achiral or meso, okay? Even after the addition of the anti-bromide across the trans double bond, if the double bond is cis and everything's symmetric, this trans arrangement of the two bromides, you can see generates what? Two stereocenters that are actually the same. This is indeed the R enantiomer, which means what? We also form the SS. And I'll leave that to you to go through that mechanism and see that, but that's the SS one right there. What I can do, and we'll look at the models here in a second, let's look at the intermediate bromonium ion. So we'll have bromonium ion up right here. And we'll have this hydrogen coming out at you. This hydrogen in the back. So you see the trans relationship between the two methyls, and then the bromide attack from the bottom. It's going to give us, opening up to give us that product, the meso. Okay? And that one we've shown there, what that's R and S. Okay? Okay. But from the Z alkene, A little bit different, right? We've got this now. Ammonium ion and hydrogens in the back. Okay, and that's the cis relationship between the two methyls, which is maintaining. And then, I forgot my plus charge. And then if we have bromide, nucleophile from below there, you see, we'll then get that, okay, which is actually the RR product. Let's look at the models. Maybe this is a little more helpful. I have a CHEM351 video too, if we have time for that. We can get to, but let's look first at the geometry of the Z alkene here. If my balls will stay in place there. So here's our pi bond, right? Here we have the trans methyls, okay? Our pi bond right here. And let's form the bromonium ion. And I kind of have to tweak my alkene, but there it would be, right here, okay? You still see the trans arrangement here. And then if we open up from below here, okay, we're going to wind up with the bromides. You see trans to each other, okay? So here's our methyls that are in the plane of the board. You see this bromide's pointing up at you, the hydrogens in the back right here. Don't forget about the hydrogens. And then we have what, bromide down and the hydrogen in front right there. So that's indeed the meso, okay? You can see that meso relationship right there. You look at it. So you can do the same thing with this one and double check that with the models and make sure that that's okay. Questions on that? Like I said, we have a couple minutes at the end, and if we still have enough memory on Isaac's phone, we'll pull up CHEM351 here and help you see that. But this is a tricky one. This is probably the toughest one to see. The geometry of the alkene translated into the products because of the specificity, we could say, of the bromonium ion. Still maintains that trans relationship, or cis, depending on which one we're looking at. And then this backside attack, popping it open, you know, you see this trans or anti-relationship right there. And you see it here too, from the cis one, for the methyls being cis, but then you have to analyze it. So that's why this, this one, the test won't have a bunch like this, okay? We could have one or two like this, where you've got to combine multiple topics, multiple concepts, and keep that straight. Okay, any questions on that? Let's go on to number 4 here, which is halohydrin formation. Halohydrin, that's a funny name, I think. Where'd they come up with that? Well, halo referring to the halogenation, and hydrin refers to a hydrate. So it's kind of like halogenation hydrate. And that's what this reaction is. It's a contraction of halogenation and hydration. And organic chemists, we love to invent new names and new words. So it's a contraction of those two terms, halogenation, hydrate formation. And that's just what it's going to be here. We're going to have, instead of just the molecular halogen, chlorine or bromide, we're going to have water also. So the electrophile is going to be the halogen, like before. And then our nucleophile is going to be the water. So let's label that. Here's our electrophilic thing that's going to take the electrons from the pi bond. And here's our nucleophile, our weak nucleophile. And what we're going to end up with, well, let's see if we can figure it out. Well, you see it there, of course. We're going to end up halogen on one side and OH on the other. But let's go through it. The halogen there is going to go through chloronium ion at that point. And you're going to have chloride, anion. But you're also in water as the solvent. And that's kind of the key. The concentration of water is super high. So you have potentially 2 nucleophiles, like chloride, like you've seen before for halogenation. But now we have a lot more of a weak nucleophile. It's neutral. Okay, so remember that did the SN1 type reactions. We said it was weak. That's okay, but this is a pretty good electrophilic thing here. We want to get rid of this positive charge. So let's go ahead and use the lone pair in water. Pop that guy open, see what we get. Well, our intermediate's going to look like this then. We're going to have the carbon-chloride bond there. And we're going to have what? Water comes along with its 2 hydrogens. Don't forget about that plus charge. It'll be that hydronium. Now, that's not the final product. what do we need to do? Use more water. We have it in excess. It's a solvent after all. So let's take that proton off like we've done before for other alcohol forming reactions. And the final product is what? The chlorohydrin. Okay, that's the specific name for that molecule. You could call it a chloro, alkanol, if you're naming that specifically. But again, that informal name, halohydrin, is where the term comes from. Combination of halogen, molecular halogen, electrophile, and the weak nucleophile, or water in this case. So let's look at some examples of that and see what we're up against there. Mechanism-wise, we've kind of covered it, but we have some other substrates here. Things might change a little bit, so let's go ahead and do trans-2-butene with chlorine and water. Okay, so again, this is reaction 4 still. Okay, so what do we expect here? Well, chloride on one side, okay, and water on the other. Okay. Now these are two stereocenters, right? You can see the trans relationship still here. You can imagine that same chloronium ion and then water attacking from the backside to open up the chloronium ion. But you could have attacked from the other side and given what? The enantiomer of this, which would have looked like this. Let's see if I can get that right. Okay. So that can also form. So it's a mixture of those two. What is this? This is the R, and this is the R. Okay. This is the SS. Okay. Now you can do the same thing with the cis one. And what do we get? Same reaction. We'll get the chloride and the alcohol. You might think, well, it looks just like that one. No, if we rotate around here, you'll kind of see it a little better. Chloride would be up there. We're drawing that as the R. One as before, but you see then we rotate around here, and we'll get this. Now, that's the also. Wait a minute, is that R also? Did I miss this one?
Yeah,
no,
I think
that's
so.
S. No, thanks for. And so this is your S, and this is your R. Okay, so good, thank you. Isaac caught that for you. And some of you probably already did too. Okay, so let's see. And this one here gives us the R and what? The R. Okay. And this is the R, and this is also R. This is the same thing. It's the same one. You can also draw out the SS that comes from this one. Okay, and it's the same idea now. Before we had the one where this was the meso one, remember? But now there are different groups on there. This one from the electrophile, that from the nucleophile. So they're all chiral, but again, formed as a mixture. It's a DL pair here. And this one, I'm not drawing out the SS, but that's also a DL pair there. Okay. You can work through that. That's a trickier concept, but I think you can follow that okay. Let's look at a simpler example, which might be this one here. Let's just look at bromine and water. So we've got this. And what are we going to get? We're going to get the trans product again, but the nucleophile is going to be water. It'll be the trans one. It'll be that one plus it's an enantiomer, but that's again the bromohydrin, the halohydrin formed from that one. Another one to look at is this one. And the question that came up there is, how much carbocation is generated at the tertiary spot? This one kind of points to this fact here. Bromine and water, now with 2-methylpropene, okay? So let's look at the bromonium ion intermediate. It'll look like this. Now, where is water going to attack? Maybe we need to do a poll here of the class. Water or nucleophile can either attack here at the tertiary position and give one type of product, breaking this bond, or it can attack at the primary spot, right? Which side do you think water is going to attack? How many people say we're going to attack here on the left? The more substitute. Okay, Isaac raised his hand. How many people say we're going to attack at the primary position? Now, what type of a nucleophile is this? Is it charged or neutral? It's neutral. So it's going to want to wait around for what? More carbocation character to form. And this is tertiary, and this is particular for the tertiary sides. We see this higher selectivity. And if we do that, that would really be a resonance structure breaking open the bromonium ion. And what? Tertiary carbocation. And it's kind of a hybrid between these two, where we talk about the attack of the nucleophile now, okay, to be that. And that's giving us what? It's giving us water at that spot. Well, hydronium ion, right? Okay. But another molecule of water, remember it's in there in excess, so then we get the attack there to give us the final product, which is a tertiary alcohol. That's where the nucleophile goes, the more substituted spot, and the electrophile goes at the less substituted spot. Okay? So that's the tertiary versus primary position. If you wrote down this product, I'm afraid we'd have to take off points. Why? That would be implying that water would be attacking at what? The less substitute primary spot. And there's less carbocation character built up there. There's a lot more tertiary carbocation character in this resonance structure. So does that answer your question about that? It was kind of the thing there. Yeah, Isaac?
So can we say then if it's a weak nucleophile, it'll attack the more substituted?
Yes.
If it's
Weak
strong,
nucleophile.
it'll attack the other one?
Yes.
Okay.
And that's similar to what we've talked about for what? SN2, nucleophilic attack, always at the less substitute spot. And then weak neutral nucleophiles always at the more substitute spot when you talk about carbocation formation in what? SN1. So this is more like what? Isaac, this is SN1 or SN2? This is more...
SN2.
Oh, be careful. Neutral nucleophile, more substitute spot. This is more SN1 or SN2 like?
I guess SN1.
SN1. You guessed right.
I can edit that out.
No, you're fine. You're fine. Okay, no editing needed. Okay, that's halohydrid formation. That's number 4. Can we do number 5? I don't know. Before we do number 5, though, there is an alternative reagent that we can talk about. Halogen molecules are kind of corrosive and dangerous. We don't like to deal with chlorine, which is a gas on its own, and then bromine's a corrosive liquid. So sometimes we use a reagent called NBS, which stands for N-bromo succinimide. I'm not even going to draw it out, because we don't know how to name succinimides yet, but that's what that refers to. And then N is for where the bromide is, N-bromo succinimide. So just know the acronym and what it does. What it is a partially positive bromide. So it provides, as this bond's polarized that way, nitrogen's more negative, so the more electronegative is to nitrogen. So it will react with alkenes such that we can get reactivity here. Let's look at our simple alkene. Instead of using bromine, we use NBS. And let's do halohydrid formation, water. And what do we get here? We get ammonium ion formation. You can see that same intermediate. Okay, but now from the NBS. And the byproduct here is the succinimide anion. Now don't worry about that. It's actually a nitrogen, which is negatively charged, but resonance delocalized there. That's kind of the end of the road. You don't need to worry about that reagent anymore. But you see the ion pair. And then what? Water does its thing just like before, and we get the bromohydrin product. Okay. And they're trans to each other. Okay. And actually, this helps deprotonate the hydronium ion. Okay. So you end up with protonated succinimide. You don't need to worry about that either. So you can either put bromine here, or you can put NBS to go to the bromohydrin. And I think I'll leave it at that. It's kind of a minor thing. It's an alternative reagent. Just use the acronym correctly on a quiz or in the test, and you'll be fine on that. All right, let's move on to reaction 5. So, reaction 5 is going to be what? Hydroboration. And we've got a few minutes here, so we can easily get through this, I think, hydroboration. And I like to talk about this from this point of view. Can we, is there a reagent combination that will give us not the more substituted alcohol, but the less substituted alcohol? And of course there is hydroboration, that's why we're talking about it. But this question mark here is an unsolved problem for us. Before, we've made alcohols from alkenes, right? But that was what? Not reaction 5. That was reaction, what, 2 up there? Hydration. If we had what? Sulfuric acid and water. What did we get? The more substituted alcohol. This is secondary alcohol in this case from 1-butene. So the question becomes, is there a set of reagents conditions by which we can switch this selectivity? Remember, we called this the Markov-Makov product. That is, the proton always went to the less substituted side. We formed the more substituted carbocation. That's where the water attacked. And we always got the more substituted alcohol. Now we're asking, can we get the less substituted alcohol? And we're going to call that the anti-Markov-Makov product. Okay. Yes. The answer is we have to use borane. And it's not boring, it's borane. It's an exciting reaction, it's not boring. Okay. Borane is what? Boron is just to the left of carbon in the periodic table there. Don't worry, Isaac, you don't need to refocus it. It's just to the left of carbon, so it has what? 3 valence electrons, and it's forming those 3 bonds to hydrogen, but that's only a total of what? 6 electrons around this molecule now. So this also brings along an empty orbital. It's Lewis acidic, we say that. It can coordinate lone pairs or react with nucleophiles. And we have a nucleophile here. We have heat. Okay, so your reagents need to include borane, BH3, and then a slash, meaning a separate operation with hydroxide and peroxide. So sodium hydroxide and H2O2 peroxide. That does the function of oxidizing the initial carbon-boron bond to the carbon-oxygen bond. And I'll show you that mechanism, but I'll really downplay that, and you don't need to worry about that. The key thing is here, borane is now our electrophile. All the other reactions have had a halogen electrophile, or what? A proton as the electrophile, and they always go on the end. The electrophile always goes here, okay? The nucleophile always goes here. And I'm going to show you that this hydroboration in reaction 5 now is really the same thing. It's just a new electrophile. And it's going to give an opposite regioselective product, the less substituted alcohol or the anti-Markov-Makov alcohol. So let's look at the mechanism here and show some examples. And yeah, it's the last topic for this chapter. And let's see what we can do here with that. So we can take hexene here, borane, and then sodium hydroxide, peroxide. Okay. So you draw those 3. Don't worry about the slash. If you leave that out, we'll know what you mean. Well, borane's BH3 here. And what are we going to get here? We're going to get the primary alcohol. Don't draw the secondary. The secondary is minor, but again, on a Quizzer test, just show the major one, and you'll get full credit there. Let's look at some other examples of it. So even a simple thing like ethylene gas, same set of conditions, you get ethanol. Okay. If you've got 2-methyl-propene, what do you get? Same set of conditions. Instead of the tertiary alcohol like before, what are we going to get now? We're going to get the anti-Markov-Makov product, the primary alcohol in this case, okay, for hydroboration. What about this one? Cyclohexene, same set of conditions. Well, here it doesn't really matter. The 2 ends of the alkene are the same. You got symmetry there, so you can guess either one and get the right answer. It's just cyclohexanol, right? So that one's not a problem. Let's look at the actual results for this one. Yes, this is the major product, but you actually get a lot of the secondary product. In fact, it's 70-30% here. You get a lot of secondary alcohol. with just borane itself. There's a solution to this. You can get almost 99% here if you change something about this reaction. What do you think it is? We're putting boron on the end there. We need to talk about that when we look at the mechanism. And if we make the borane more bulky, if we put two bulky alkyl groups on there, we might be able to increase that. So if we use what's called 9-BBN, I'll show you that structure here. Instead of borane, we'll get 99% of the primary alcohol. Now don't worry about that for the purposes of our class. You can use either borane, BH3, or 9-BBN, okay? But always show what? The anti-Markovnikov alcohol product. Okay, let's look at the mechanism and the borane variation here in the 9-BBN. We've still got a few minutes. Our mechanism here. So what are we talking about? So here's our borane, and we draw it with its empty orbital, okay? So let's see. We can then take the pi electrons, that's our nucleophile after all. Here's our electrophile, the empty orbital on boron. And let's just stop right there. Let's just see what that looks like here, mechanism-wise. We'll form that bond between carbon and boron, and it's got the 3 hydrogens still on there. And if we pull these electrons out of the pi bond, this carbon here is bonded to boron. But what happened to that carbon? Am I missing something here? What am I missing on this intermediate? Anybody have any ideas? I need what?
Carbocation.
Charges, yeah, carbocation is going to be right here. And what about the charge on boron? It's now got 4 groups. Do your formal charge calculation. What should this charge be? Negative. It's a borate, okay? Well, how can I get rid of this positive charge and this negative charge? Let's do a shift here, okay? It's now a hydride shift, okay? Hydrogen with its pair of electrons is called hydride, or negatively charged thing. It's not floating around as a negatively charged hydrogen, but it's migrating over, and that will give us this hydrogen, okay? And then, like I said, the next step here is the hydroxide and the peroxide, and that will give us what? The alcohol product. Okay? Now, why is it the primary alcohol product? Let's see. We could imagine borane adding to this spot, and then we'd get what? A primary carbocation. But if we put the electrophile at what? The end position, the less substituted spot, will generate the more substituted carbocation. Okay. Now that's not the true mechanism. What's actually thought of the mechanism and how it actually works is this. It's actually thought to be concerted, but there is some partial positive charge that builds up at the transition state, and you should always think of that at the more substituted position. So you can think of it as concerted, just one step where bond making, bond breaking happens all at once, or this, doesn't matter, but that accounts for the regioselectivity, anti-Markovnikov product. Okay, let's look at one more cyclic example where it's a little bit tricky here. And then we'll do some synthesis problems, and then we're done. So we're almost done here for the lecture class period here. What have we got? Borane, BH3, sodium hydroxide, peroxide. Okay, and now we have methyl, cyclopentene. And so what are we going to get? We're going to get the boron going to the less substituted side, okay? And I already went ahead and added that hydrogen there, okay? So that would be correct. It's not the other way around, where you have boron on the more substituted side and hydrogen on the less substituted. Why? Because there's more carbocation building up there, and that's where the hydride migrates to, okay? The electrophile was the boron, the borane, and that goes to the less substituted. And then if we do the oxidation step, we get this. We get the alcohol, the less substituted spot. That's indeed anti-Markovnikov, okay? And we get the hydride there, okay? So that's our product. Don't put this one, okay? If you put that alcohol that's what, at that tertiary spot after the oxidation, we take off points. So make sure you get the right regioselectivity. Now, the question is what? What else do we need to talk about here? These are two stereocenters. Are they going to be trans to each other or cis? That's a deeper level of understanding, and the observation of this process actually led to a refinement of the mechanistic understanding. Let's show you what the true product is. It's where the methyl is down and the alcohol is up. They are indeed trans to each other. So you may want to think about why that occurs. Let's get a little three-dimensionality going here. So if we have our borane and our empty orbital here on boron, let's go ahead and add it there, and at the same time add our hydride from the same face, both from the top face. We call it syn addition, where they're both coming in together. That will give us what product then? That will give us hydrogen up there, you see. That methyl will be forced back in what? The borane will be up also. Bring that hydrogen back. Okay. Well, what does that say about the next step? Okay, that kind of confirms the syn addition of the hydride and the boron adding from the same top face. Okay. So you see they are indeed cis to each other in the product, intermediate really. But now what about the oxidation of the carbon-boron bond into the alcohol? You see the methyl is down. The boron's up here. They're already trans to each other. And so we retain, okay, that stereochemistry is retained by the oxidation. So let's see, I don't really have time to do the mechanism of that. I've never put the mechanism of the oxidation on a quiz or a test, but don't tempt me. I could put it on there. I can show you how that works, maybe if we got more time next time. I really want to get to some synthesis applications. Well, maybe I can show you real quick just from this. The peroxide actually forms the peroxyanion here. Hydroxide is strong enough base to pull a hydrogen off peroxide to give you the peroxyanion. And that adds to the borane intermediate here, which looks like that at that point, right? Another borate. And then we get migration from the same face, from boron over to oxygen, and we lose hydroxide right there. I guess I am showing you the whole mechanism. I didn't want to do that, but it's so much fun. I guess I had to do it. There we've got that. We've got now this on oxygen, you see. And we've got, you know, the migration over there. So we've got the H2 still there. And we've got, what, OH hydroxide coming off. And so you see the trans relationship there is still there because of the retention of that stereochemistry, that migration from boron to oxygen goes there. And why does this work? Well, oxygen-oxygen bonds are very weak. So this migration is favored there. That gives this product, which is then just hydrolyzed with water. I won't do the rest of that step. You can imagine water adding to boron and then a migration to get a proton on oxygen there, make the element. That's probably enough that you need to know there. Oh, the other reagent I needed to show you was what, 9 bbm. So let's show you that real quick and do a couple synthesis problems. Then we're done for this video. Hang in there. So 9 bbm, what's that? Another acronym, right? 9 bbm. And you can just say that on a quiz or a test in combination with the peroxide hydroxide. Drawing the whole thing out is a little tricky. This stands for 9-bora-bicyclononane. So I'll show you the structure. It looks like this, where we've got a bicyclic structure and just one hydride on boron. But that's still neutral, okay? So 9 bbn still has the empty orbital, it still can be Lewis acidic, but it's got these big bulky R groups here, which is going to do what? Favor even more of the anti-Markovnikov product. So this is the one that goes up to 99% for the primary product. It's formed easily from this reagent, which also has an interesting name. Stop sign dialkene. No, that's cycloocta diene or cod, and you just treat borane itself, and I'll let you worry about that mechanism. It's just 2 hydroborations across the ring here, and then all the other carbons are part of the 9-BBN. So it's kind of a fun thing to look at. But all you need to do is use it to give more of the primary antimarcotic alcohol. Of course, for a quiz or a test, you can just use the borane, the BH3 itself. There won't be a problem. Okay. Let's do a couple synthesis problems and wrap things up real quick. The synthesis problems allow us to do a number of reactions. So let's pose some challenges here synthetically. And again, we've learned a lot of reactions, so we're able to solve a lot of synthetic problems here. So let's see. Can we take this secondary bromide and convert it into, somehow, into this alkene? Now, that's not a direct transformation we've covered yet, right? Well, is it? It's a what type of reaction would you think about here? Can we form an alkene directly from a halide? Remember from chapter 8, was it? E2 reaction. So what would we use here? Yeah, TB-toxide, the bulky strong base, would do that directly. And it's Zaitsev's rule, the more alkene. So we want to pull a proton here at that adjacent position. Or we could convert this to what? Convert this into an alcohol. And we could do that with water, okay? That would be what, an SN1 type reaction. And then we could dehydrate this with what? Strong acid, okay? We could also take this alcohol that we could get from the halide and convert it back into a good leaving group, okay? And then do what? All of the charged nucleophiles and things here to do what? More SN2 chemistry, okay? So you can see how these things kind of work together here to form a variety of products. Let's look at another, maybe more challenging transformation here. And this ties into another functional group we've talked about. Can we convert the alkene here into this? What do we call that? The cyclic ether, that's what functional group again? Cyclic ether, it is an ether, oxygen, 2 carbons on it. That's what? Epoxide. Okay. How do we do that? We're starting with an alkene here. What can we convert that alkene into? Well, we can convert that into what? The bromide with an alcohol on here. That's one of the 5 reactions, right? The bromohydrate. What are the conditions for that? Well, that would be bromine and water. Okay. And then what? How do we go from here to the epoxide? Well, we do have a leaving group, and we do have a potential nucleophile here. It's neutral right now. Can we convert that alcohol nucleophile into something that's stronger, more charged? Yeah, we can use a strong base, sodium amide, or sodium hydride, but it's got to be a strong enough base. TB-toxide will actually do this as well, but these pKs are much higher, the conjugate acids, so maybe you want to use that to deprotonate that. And you see if we can deprotonate that, then we're set up for what? The O- and the bromide, which is a leaving group. What? This can then function as a nucleophile right there being charged, backside attack will give us that inverted stereocenter right there for the epoxide. Okay, what about one more here? Synthetic challenge, then we're done. Let's take this alcohol and convert it somehow. Think about how we might do this into the dichloride, trans dichloride. Sometimes these are better to think about them in the reverse direction. How can we make this? Well, we make it from the cycloalkene, okay, pentene, and what? Just chlorine. That's all you need there, okay? Anti-chloride. Don't worry about the other enantiomer of that. We're just, making one or the other with the translation. Well, how do we go from the alcohol to the alkene? Well, we can dehydrate it, right? Sulfuric acid, or what's the other way to dehydrate an alcohol? POCO3. Okay, and that will give that there. To start out on chapter 11, next time I'll review maybe a couple other quick synthesis examples. That's what these are, multi-step synthesis examples. They're a little bit trickier, and we'll review all 5 of the big H reactions before we plunge into chapter 11, which will be alkynes. We'll do the same electrophilic additions with the pi bonds with alkynes next time. So stay tuned for that. Look at Learning Suite for updates of everything. We'll give you URLs to everything and keep messages and everything up to date. We'll need to talk more about how we're going to handle quizzes and the exam coming up as well. So very good. We'll see you next time. Thank you.